In this video, I'm going to show you why functional programming languages can do anything normal programming languages can. To do this, we'll use Turing Machines, the Lambda Calculus, and this tool that I'm developing to help visualize these things. To a programmer, this is a function. Here, we're creating one called add that takes in two things, a and b, and returns their sum. Pretty simple. And this is an object. This is a representation of a car, so it stores values like its make, model, year, and fuel level. It also has a few of what are called methods, or like things you can do to a car. So for example, drive might lower the gas and refuel might raise it. But that's just a representation. This is what it actually looks like in code. And hopefully, even if you haven't programmed before, you can see like where the values are and the methods and their behaviors and stuff. These two ways of coding, functions and objects, are very useful, but obviously they have their different use cases. But what if you liked programming with objects so much that you wanted to create a whole language where everything is an object? Well, that's been done. In Java, everything, almost, is represented as an object. Like the number 1 has a value, 1, and some methods like add or subtract. Okay, sure, that seems reasonable. I mean, you already basically have functions, they're just called methods. But what if you wanted to do the same thing with functions? What if you could make a language entirely out of functions? No numbers, no anything, everything is represented with functions. If you're anything like me, at first this sounds impossible. Like, you're trying to tell me the most complex scheme of inheritance, classes, loops, and other patterns can all be represented as just functions? Yes, they can. Well, there's a subtle difference in what I'm actually saying. What I really mean is that if you give me a program written in any language, even an object-oriented one like Java, I can make a program just made out of functions that gives identical outputs based on the same inputs. Like, if you have a program that drives that car from earlier a few miles, you can write an object-oriented program using that car object, and I can basically write a huge function that does the exact same thing. But there are some things that aren't allowed. Like, there can't be any what are called side effects, like printing to the console or updating a user interface, or basically anything that's not just returning an output. The reason for this will become clear in a bit. This seems pretty limiting, like you can't really make web pages or stuff like that. But I actually think it makes it even more fascinating. Like, this is basically it. This is all we have to go with. So, how is this possible at all? Well, first, we should find a way of talking about the capabilities of these two things mathematically. Quick history lesson. In 1936, a guy you might have heard of called Alan Turing came up with the idea now known as the Turing Machine. This theoretical concept was designed to calculate anything a human could. It's given a set of rules that instruct the machine to just basically calculate whatever you want. This started as just a math concept, but decades later, when the first computers and programming languages were being developed, they, including Java, were actually based on this idea. Nowadays, programming languages are classified as Turing-complete if they can evaluate anything a Turing machine can. So, we're going to try and figure out if functional programming languages can be Turing-complete. But what is a functional programming language mathematically? Well, functional programming languages are based on a concept developed right around when Turing machines were, actually by Turing's advisor, Alonzo Church, and this concept is called the Lambda Calculus. Church originally wanted to make a new system of logic that bypassed the recently published Gödel's incompleteness theorems, but this actually ended up not working out. Through the decades, Lambda Calculus evolved into a more formal and simplified system, and it's actually what functional programming languages are based on today. The Lambda Calculus actually has nothing to do with your normal differential and integral calculus, but it deals with pure logical functions. A lambda function takes one input, returns one output, and has no side effects. A side effect, like I mentioned before, is basically doing anything outside the scope of the function, so like printing to the console or even adding something to a list. Side note, functional programming languages can actually get around this by using another math concept called monads, which sort of like quarantine off the contaminated side effects. But sadly, I can't get into that in this video because that would take way too long. In a program, every variable's current value taken together is called the program's state, and it's essential to the definition of a Turing machine. And it seems like the Lambda Calculus doesn't really have a way of handling state, or variables at all. But astoundingly, as they proved in the Church-Turing thesis, the Lambda Calculus and Turing machines are actually equivalent systems. Defined formally, that means a Turing machine can evaluate any lambda expression, and a lambda expression can evaluate anything a Turing machine can. And that is what I'm going to show in this video. First, I'll define what a Turing machine is, then I'll explain what Lambda Calculus actually is. Then once we've done that, we can actually go about constructing a Turing machine as a lambda expression, proving Lambda Calculus is a Turing machine, and thereby proving that any object-oriented program can be written in just functions. To prove it the other way, that Turing machines are the Lambda Calculus, you would have to program a Turing machine to calculate any lambda expression. This was actually done by Turing back in the day, but in my opinion the proof is incredibly tedious and boring, so I won't cover that in this video. So let's begin. What is a Turing machine? Well, you can think of a Turing machine like an infinitely long strip of paper divided into cells. Each cell has a symbol on it that can be changed by a head as it travels along the tape. The machine also has a state register, which is usually just represented as a letter. It has a table of instructions where each row has a possible state and the symbol under the head, and then based on those, some directions, like change the symbol or move to the right or left. It can also switch to a different state after it's done. It comes with a starting tape configuration, a starting state register, and an ending state, which whenever it reaches that state, it just stops. Okay, let's actually look at an example of a Turing machine. Here's a nice simulator I found online, and I'll link it in the description if you want to use it. This one is more mathematically pure, so it only allows one print and one movement per instruction. Let's look at this simple program. It starts with state A in the register, and the first square is blank, so according to the table, it prints 0, moves right, and changes the state to B. Now, because the state is B and the cell is still blank, it prints 1, moves right, and changes the state back to A. And because there's no ending state, it just repeats 0, 1, 0, 1 forever. Conceptually, you can hopefully see the similarities between a Turing machine and a modern computer. The table is like a program, the starting configuration is like the input, the tape is like the memory, and the tape once it's done is like the output. So basically computers are just more user-friendly Turing machines. Okay, so this is what we need to construct within the Lambda calculus. But what actually is the Lambda calculus? This is what I'm depicting as a lambda function. You can see it takes an input and kind of flows down into the right into the output. And this is what standard lambda notation looks like, but using it can get kind of crazy really quickly, as you'll probably see soon, so I'm going to stick to using this visual representation. By the way, in the description I put a link to this tool that I made to help visualize these functions, so at any time feel free to pause and play around to get a better understanding. Okay, so what is this thing? Well, this is a lambda function, probably the simplest. It takes one input that I've colored red and its one output, which is also red. Notice if I put some variable, orange, into this function and click beta reduce, the whole expression turns into just orange. This is what's called the identity combinator, and its output is the same as the input. By the way, what I just did there was called beta reduction. Beta reduction replaces all instances of an input's color with what's being inputted. Okay, now let's look at this slightly more interesting function. If we drop yellow into it and beta reduce it, we get another function. And this function takes in another input. But look, no matter what that input is, it'll always return yellow. And look, I can actually put in two inputs at the same time, and when I hit beta reduce twice, it always gives back the first input. Notice what just happened. We basically created a function with two inputs using functions that only take one. How? Well, we made a function that returns another function. This is called currying, and it's really useful because it lets us create functions with multiple inputs. This function also has a special name, the k combinator, and it always chooses the first of its two inputs. And these boxes that I'm throwing into these functions are actually functions themselves, because in the lambda calculus, literally everything is a function. So we can pass k and I into k, and look what it makes, k. This k and the k from earlier might look different, but they're actually said to be alpha equivalent. That just means the colors are different, but they do the exact same thing. To make things less cluttered, in this tool you can convert a beta normal expression, which is just one that's as beta reduced as possible, into what's called a combinator. Combinators aren't actually part of the lambda calculus, it's just a way to simplify expressions visually. Okay, so how do you actually do things with these expressions? How do you make numbers and stuff like that? Well, let's start with something a bit simpler first. Booleans, like true and false. We already actually have an encoding of true, the k combinator. In what's called the church encoding, true is a function that takes two inputs and returns the first. This seems kind of random right now, but this will be useful later. Similarly, false takes two inputs and returns the second. But why define them like this? Well, think about how an if statement works. Our variable bool here is true, and the if statement is basically picking the first option out of two lines to run. If it were false, it would be picking the second one. So, church booleans are basically built-in if statements. True will always pick the first option, and false will always pick the second. If we wanted to make this a function, we can do something like this. By the way, this light blue box represents the output of putting orange into whatever red will be. If this function is given true, it'll pick the first one, orange, but if it's given false, it'll pick the second, yellow. But remember, orange and yellow both represent whole expressions, which basically means we have functional if statements. So, using this property, let's try and make some logic gates. The simplest is probably the NOT gate, which just returns the opposite of the input. We know the input will be a function that either selects its first input or its second input. And remember, this blue square is the result of applying the first input, so whatever we give it is like giving the curried function its second input. Okay, so if the input is true, it'll select the one on the left, and if it's true we want it to return false, so we can give that input false. And look, if we put true in it and beta reduce it, no matter what the second input is, it'll always return false, which is exactly what we want. And if red is false, it should return true, so we can put true into the input on the right. And look, when we put in false, it returns true. So there we have a functioning NOT gate. Let's do one more, AND. This one's a bit more complicated, so we can pull up the truth table and look at it one input at a time. Notice if red is true, the output is always the same as orange. So we can set it up the same way as we did for NOT. We can give red 2 inputs, and depending on if it's true or false, it will select the first or the second. And we just figured out that if red is true, the output is always orange, so we can put in the first input as orange. And if red is false, we know the output has to be false no matter what, so we can put false in on the right. As for the last one, OR, go ahead and try it on your own. And remember the tip to look at each input individually. Tell me in the comments how it went. Booleans are pretty cool, but we can go further. How about numbers? Well, Church came up with a really clever way of encoding them, so let's look how he did it. Here are the Church encodings of numerals 1, 2, and 3. You can see every numeral takes 2 inputs, and we can call them an operation and a value. The output puts the value through the operation n times, like 2 pushes orange through red 2 times. If it helps, you can try to think of these like once and twice instead of 1 and 2. But you can see these get pretty big defining them on their own, so it'd be much easier if we could have a function to find the next highest number, a successor combinator. Okay, what this function needs to do is basically repeat the operation one more time. You might think we can just apply the operation to it again, but we have no way of knowing the color that the operation was defined with. Its scope is kind of contained within the numeral. So, here's how we can get around it. Inside of our function, we can create our own dummy operation and value, orange and yellow, that we can use to construct our own dummy numeral. Because red is a numeral, it describes applying an operation to a value red times. So we can sort of catch our dummy numeral up to speed by giving our dummy variables to red. Red will take them and apply yellow to orange red times, which will be alpha equivalent to red. But now we know the operation that it's created with. So we can take our dummy numeral and apply the operation, orange, to it one more time. And there we have it, the successor combinator. It might look like this function takes 3 inputs, but that's only because the numeral itself is a function that takes 2. Don't believe me? Watch. We can put in 1, beta reduce it. Now we supply our dummy function and value, and boom, 2. Or, more precisely, this function is alpha equivalent to the Church numeral 2 we defined earlier. Okay, so we can find the successor to a number, but can we add? Well, we can use the Church encoding to our advantage yet again. So what we need to do is to find the successor to orange red times, right? Because that's all adding is, repeated succession. And luckily, we already have a function that applies an operation to a value a certain number of times, the Church numerals. So if we feed into orange the successor combinator as the operation, and red as the value, it will basically add 1 to red orange times, which is the same as adding red and orange. Multiplication is also pretty similar, but this time we want to repeatedly add. Multiplying red and orange is like starting from 0 and adding red orange times. So the function we want to repeat is adding red, and the number of times we want to repeat adding red is orange. So we can put the add combinator with red as its first input into orange, and the second input should be what we're starting with, which is 0. But what is 0? Well, if 1 applies an operation to a value once, 0 should apply an operation to a value no times, so just return the value. So we can put that in as the second input, and there we go, we can multiply. And you can keep going like this to find exponentiation, so I would recommend trying this out on your own to check your understanding. Okay, hopefully you have a pretty good understanding on how the Lambda Calculus works. And now we can get at the big question. How on earth is this thing Turing complete? And I'd recommend going back and rewatching the Turing Machines section, in case you need a refresher on how everything works. Remember, what we want is if we are given a Turing machine, we need to be able to construct a lambda expression that gives us the same output for every input. So to do that, we need a few things. We need a tape, an alphabet of symbols, a way of representing the table of instructions, and here's the big one, evaluating those instructions as the state changes through time. I promise you this is possible, and the way we do it is one of the coolest things in this field. So let's get into it. First, let's create a set of symbols, or an alphabet. We do already have a set of symbols, the Church numerals, but we can actually do something a lot simpler. Let's say we want our alphabet to have 3 symbols. Probably the simplest way to do this is to have a function with 3 inputs, and then each input corresponds to a symbol. So this will be the first symbol, this is the second, and this is the third. This is called the Scott encoding because it was made by a guy called Dana Stewart Scott. We also have to assign a symbol, let's say the third one, yellow, to represent an empty cell, and we can call the first 2 0 and 1. And if your Turing machine needs a longer alphabet, no worries, just add more inputs. Now, how do we encode the tape? Well, we need a way to represent a list of symbols, or what I'll call a string. We also need a way to easily get the cell under the head and to actually move the head along the tape. I think it's a good idea to wait until we have a game plan for these last two things before we actually define our encoding for a string. Okay, so one kind of not obvious way might be to separate the tape into three separate strings, one representing the tape to the left of the head, one being just the symbol under the head, and another being the tape to the right of the head. We can combine these three strings, which we'll define later, into one expression by applying them all to some expression like this. That way, kind of like true and false earlier, we can select which string we want by putting in a function like this. Okay, let's think about how we might perform instructions on this tape. Let's start with probably the simplest instruction, just changing the symbol under the head. To do this, let's make a function that takes in a tape and just returns another tape, but with the current cell changed. We can get the left of the original tape by just giving it a function that selects the first out of its three strings. Then, we can just put that in as the left of our new tape. The next input represents the current cell, so we can put in what we want to change it to, let's say 0. And for the last input, we can get the right tape in the same way we got the left tape earlier, and feed that in. Okay, great, so this function takes in a tape and returns another tape with 0 written to the current cell. Now let's look at a more complicated instruction, moving the tape. If the tape moves to the right, the strings will change like this. The current symbol is added to the end of the left string, the first symbol is removed from the front of the right string and set as the current symbol, and if it moves to the left, the opposite. Okay, let's try to encode this movement. We can't really define appending to a string until we know what a string is, so for now we can have a placeholder function. Next, we have to figure out how to get and remove the first symbol in the right string. Remember how we defined the alphabet? Well, these symbols look a lot like true and false, but these ones can select from more than two inputs. Look, if we create three expressions and pass them into a symbol, it can select whichever expression corresponds to that symbol. Let's say somehow you got the first symbol to the right of the head. We can pass in three different tapes that are the results of moving to the right, depending on what the symbol is. Like, if the last symbol is 0, we want to change the current cell to 0. So, we can put in this function that we defined earlier that does exactly that. Of course, we'll have to give it the original tape too. We can put in the two other copies of this expression, where it changes the current cell to whatever symbol it corresponds to. And we can even use our append function from before to update the left string. Okay, now might be a good time to figure out what these strings actually should be. We want to be able to put in expressions as inputs to the first symbol like we just did, and once it's removed, we need to be able to do it with the next one too. One way we can do that is to have the rest of the string stacked on top of it like this. That way, if the first is removed, it still looks like a string. But one thing we didn't think about is how the tape actually extends forever blank in both directions. This is a problem because infinitely long expressions aren't actually allowed in the Lambda calculus. One way to fix this is to say that if it ends with a blank symbol, it just extends blank forever. But that brings up another problem because on the left side, the tape starts with infinite blanks. But we can actually get rid of this in a really clever way, by reversing the left string. That way, a string's first symbol is always the one right next to the head. And look, if we actually put these expressions into the string we just defined, the rest of the string is being applied to the chosen expression. And that means we can give the expression the rest of the string as an input and use the right string for a new tape. Okay, so if we actually want to transform a tape by shifting the head, we'll need to apply three versions of this function to the side we're shifting to. Like, if we're shifting to the right, we need to apply these functions to the right tape, which, remember, we can get by doing this. And now that we know what strings look like, we can figure out how to add a symbol to the beginning of a string. And remember, we don't ever have to add to the end because we reverse the left side. This is a bit trickier than you might think because the rest of the string needs to be applied within the function. So we can do something similar with what we just did with getting the last symbol. There are only three possibilities for symbols, so we can select a new string from the three possible outcomes. And that should do it for our append function. Okay, so we have a tape and a way to move the head around the tape, but there's one more component of a machine's state that we haven't included yet, the state register. Together, the state of the register and the state of the tape are referred to as the machine's configuration. Encoding the register is actually pretty simple, because it's just another symbol. We can use the Scott encoding again, but with a different alphabet, where the number of inputs is the number of possible states. Combining it with the tape is pretty simple too. Let's just add the register state, for example Q, to the end. And here we have an encoding for a machine's configuration at a specific point in time. And for future reference, it's really important to remember that the inputs always go in this order. Tape to the left, current cell, tape to the right, and then the state register. Great, we can encode configurations. Now we can finally look at how to simulate state. To reiterate, state is basically a snapshot of a program in time. Like, in this program that finds a factorial, answer starts as 1, and with each iteration, answer changes to a new value. And in a Turing machine, the configuration is the state that changes through time. Obviously, we don't have for loops in the lambda calculus, so we'll have to find another way. A lot of functions, like this factorial, can be rewritten using something called recursion. In recursion, the function calls itself at a lower value over and over again until it reaches what's called a base case. This looks a lot more feasible to implement than a for loop, but there's one problem. The function uses its own name inside the definition, and we can't really do that in the lambda calculus. We do have combinators, but remember, those aren't actually part of the calculus. But don't lose hope, there's a way to get around this. We need something called a fixed point combinator. Here, f is a fixed point combinator. What's special about this is when it's given an input and beta reduced, it returns its input applied to itself. And you can keep on beta reducing it like this forever, and it will just keep on applying its input. Okay, given this hypothetical combinator, let's try to construct a function that when it's fed into the fixed point combinator, it finds the factorial. So when you're making a recursive function, usually the first thing you do is define the base case. So to make the base case, we need a function that returns whether or not its input is 0. And I do recommend you try this out on your own, so you can pause and do that, but this is the one that makes the most sense to me. Look, if we put in a number like 2, it returns false, but if we put in 0, it returns true. And remember this, the if statement? Here we can create a function that will do one of two things depending on if it's at the base case. If it is, we want to return 1, but if it's not, we return the number multiplied by, well, we have to use the factorial function, which we can't because that's what we're trying to define. How about we change up this function so it takes itself as an input? That way, we can reference it without using the function name. This is pretty much just putting off the problem until later, but let's see where this takes us. And if this is the factorial function, we want to pass in the number -1. I haven't gone over how subtraction works, but this is another thing you could try on your own. It's pretty tricky though, so I'll put a solution in the description. Okay, so now we have a perfectly legal lambda expression that computes the factorial. It just needs itself as an input to run. But that is exactly what the fixed point combinator lets us do. So if we define this pseudo-factorial function as p and put it into a fixed point combinator, then put in some numeral like 2, f applied to p turns into p applied to f applied to p, because that's how the combinator works. Now, you could keep expanding this into an endless tower of p's, but in order to get this kind of stuff to work, the lambda calculus uses what's called lazy evaluation. That means something isn't reduced until it's absolutely needed. In this case, after only one beta reduction, we can feed f applied to p along with the numeral 2 into the pseudo-factorial function. And we can expand that into this, which looks kind of crazy, but watch. Okay, is 2 0? No, so we only have to worry about this part. And look, we can't really do anything without expanding the fixed point combinator, so let's go ahead and beta reduce it. And just like that, we've completed a step of recursion. We keep going until it gets to 0, when it returns 1 and the recursion stops. Now we just have to evaluate the expression, and boom, we just did recursion. Now we just have to figure out what this fixed point combinator actually is. Okay, the intuition for this is pretty shaky, and this was probably only discovered with lots of messing around, so just bear with me. If you play around with the lambda calculus enough, you might come across this function with some interesting properties. If you feed it some expression, it applies it to itself. And if you feed it itself, it does this. And you can keep doing this over and over and it will never reach a beta normal form. This is called the omega combinator, and it's an example of a divergent expression. It's just one that doesn't have a beta normal form. But this isn't very useful because it doesn't do anything. We need some way of repeating another function along with it. And with some more messing around, you might arrive at this function. And look what happens when you give it an input. It's alpha equivalent to the input applied to the function. And yeah, that's a fixed point combinator. This one specifically is called the y combinator, and it's probably the most well known. So we can finally define our full factorial function by using the y combinator and our pseudo-factorial function like this. Now, how can we use this to encode state in a Turing machine? Well, like how we transformed factorial into a recursive function, we can do the same for the table of instructions. This function needs to take a configuration as an input and give the final configuration as the output. And the entire Turing machine will just be this function with one input. But just like with factorial, we're going to need a helper function to do most of the work. This is what we'll call the transition function. And just like factorial, to make it recursive, it needs to take in itself as an input. Of course, it also has to take in a configuration. Then, it'll match up the state register in the current cell to a set of instructions, like in the table, and then run those instructions. Actually, we can run pretty much any kind of instructions a Turing machine can. We can write to the current cell, and we can move the tape around. So, all that's left to do is figure out which instructions to run based on the register in the current cell. Let's start out by ignoring the register at first and just looking at the tape. Let's say, if the cell is blank, we should print 0. If it's 0, move to the right, and otherwise, set it to the final configuration. That means that the program will have to stop. Remember, we can get the current cell by giving the configuration a function that selects its second input, like this. And the current cell itself is a function that selects from its inputs. And just like how we've done before, we can give it the 3 possible tapes from the transformation. And remember, if we want to move the head, we have to feed the function into the side we're shifting it to. But this doesn't have recursion. All this does is return another configuration. In our setup, if the cell is blank or 0, we need to return the helper function applied to the new configuration, just like how we did in factorial. So we could just do this, because red is the helper function, but in some cases we need to stop the program, like if the register is set to the final state. We can solve this by only applying the recursion to the tape that we want to, like this. Okay, great. That should work for just looking at the tape. So now we can do something similar for the state register. As you probably know, this will select the register's state. And remember how we defined the state register? It acts just like a symbol, so we can do the same thing, feed the resulting tapes for each of the states into the function. The resulting tape depends both on the state register and the current cell, so we can put in what we just did. And this finally makes up our helper function, so all we have to do now is feed it into the Y combinator, give it an input, and define the Turing machine combinator. If you're still watching this, huge congratulations. I'll remind you what this means. The Lambda Calculus is a system made up of only functions, and it's the basis for functional programming languages. And a Turing machine is the system that's the basis for pretty much all non-purely functional programming languages. By showing that it's possible to construct a lambda expression that evaluates equivalently for every input for a Turing machine, we have just proved how functional languages are able to compute anything non-functional languages can. The proof in this video is based off of a paper that I'll link in the description. I really hope this video has given you a good understanding of the Lambda Calculus, as well as the basics of Turing machines. Again, thanks so much for watching.